Figure 1 shows a sketch of a curve C with the equation r equals 1 plus tan theta for values of theta between 0 and pi by 3. And that given domain is going to be important shortly. Figure 1 also shows the tangent to C at the point A. The tangent is perpendicular to the initial line. Use differentiation to prove the polar coordinates of A are 2 pi by 4. We know that if we work in polar coordinates, that x is equal to r cos theta and y is equal to r sine theta, and that's just basic right-angled trigonometry. So, given that r is 1 plus tan theta, x is going to be 1 plus tan theta times cos theta, which is going to be cos theta plus sine theta. Y would be 1 plus tan theta times sine theta, and so that is going to be sine theta plus sine squared theta over cos theta. From there, dx d theta is going to be negative sine theta plus cos theta. Now to do dy d theta, we've got to take into account that we have a quotient just here. U is equal to sine squared theta. V is equal to cos theta. So du d theta would be 2 sine theta cos theta, and dv d theta would be negative sine theta. So dy d theta is going to be, well, differentiating the sine just gives us cos theta. Then we've got the quotient. So it's going to be v du d theta. So that's 2 sine theta cos squared theta. Take away u dv d theta, and with the negative just there, that's going to make it into a plus. So it'll be plus sine cubed theta all over v squared. So that's going to be cos squared theta. Now, let's put dy d theta over a common denominator. And so what we're going to have is cos cubed theta plus 2 sine theta cos squared theta plus sine cubed theta all over cos squared theta. Now dy dx is equal to dy d theta divided by dx d theta. So that is going to give us cos cubed theta plus 2 sine theta cos squared theta plus sine cubed theta all over cos squared theta, and that cos squared comes from here, times cos theta minus sine theta, which is from up here. Now, for the vertical gradient, the vertical tangent, that means that the denominator of dy dx must be 0. So it's going to be cos squared theta cos theta minus sine theta equals 0. Now, in the domain given, this one is not going to be 0. It's not 0 until we get to pi by 2. So it must come from here. Cos theta take away sine theta is 0. Cos theta equals sine theta, and that happens when theta is equal to pi by 4. The cosine of pi by 4 and the sine of pi by 4 are both root 2 over 2. So that's in the given domain. And so, if theta is equal to pi by 4, we get that r is equal to 1 plus tan pi by 4. Tan pi by 4 is 1, so that is equal to 2, and that implies that our point is 2 pi by 4 as required. The finite region R, shown in the above diagram, is bounded by the curve C, the tangent at A, and the initial line. Use calculus to show the exact area of R is a half 1 minus log 2. Now we know that A in polar coordinates is 2 pi by 4. It might be useful to know those in Cartesian. So x would be equal to 2 cos pi by 4. So that's 2 root 2 over 2. And therefore that's root 2. And y is going to be 2 sine pi by 4. And we know, of course, that sine pi by 4, cos pi by 4 are equal. So that's root 2. So in Cartesian, this point up here is root 2, root 2. Now, we're after this area R. Now, we have a triangle just here like this, which would be root 2 and root 2. If we consider the integral from theta equals 0 to theta equals pi by 4 of a half r squared d theta, that is actually going to give me this part. So to find r, we're going to want the area of the triangle, which if I call this point x, is the triangle OXA. Take away the result of this integral. So let's go ahead and do the integral with the information that we have. So that is going to be half the integral from 0 to pi by 4 of 1 plus tan theta squared d theta. So that's going to be a half integral from 0 to pi by 4 of 1 plus 2 tan theta plus tan squared theta d theta. Now we know that 1 plus tan squared is sec squared. So this is a half times the integral from 0 to pi by 4 of sec squared theta plus 2 tan theta d theta. And we can integrate both of those things. So that is going to be a half. Sec squared integrates to tan, so we've got tan theta. Then, if we think about integrating tan theta, it's the integral of sine theta over cos theta, which we can think of like that, and then the top is the differential of the bottom. So it's negative log cos theta, or log sec theta, whichever way you want to look at it. So it's take away 2 log, I'm going to look at it as cos x. Don't need to worry about the modulus because we're between 0 and pi by 4, and the cosine is going to be positive in there. So using the top limit, we get 1 take away 2 log root 2 on 2. The bottom limit is just going to give us 0. Tan of 0 is 0, cos of 0 is 1, but then the natural log of that is 0. So that's going to give us a half into 1 take away log, and this will end up being a half because we've got root 2 squared over 2 squared, which is 2 over 4, which is half. And that's taking the 2 in there using the log law. And we can rewrite that using this as a half is equal to 2 to the negative 1. We can rewrite that as a half 1 plus log 2. Now let's go back to what we discussed about the area. The area of this triangle up here is a half times root 2 times root 2 is equal to 1. So the area we want is 1 take away a half 1 plus ln 2. So that's 1 take away a half ln 2, which is a half 1 take away ln 2 as required.